Now time for example number 2. We're going to find where f of x equal x over x squared minus 1. It's concave up and concave down, and we're going to find any inflection points. Again, we're looking for the second derivative, so we've got to start by finding the first derivative. And for the first derivative, we're going to have to use the quotient rule. We're going to square the denominator. So it's going to give us x squared minus 1 quantity squared. And then in the numerator, we're going to have the derivative of the top, so that's 1 times the denominator, x squared minus 1, minus x times the derivative of x squared minus 1, so that's 2x. And now, when we were first just finding derivatives, I told you not to simplify anything, but now because we're going to be using the derivative to find the second derivative, we want to simplify as much as possible. So in the numerator, we're going to multiply out and simplify, and that's going to give us x squared minus 1 minus 2x squared. The denominator we're leaving alone exactly as it is, and we're going to end up with negative 1 minus x squared in the numerator over x squared minus 1 quantity squared in the denominator. So there's the first derivative. That's the good news. The maybe less exciting news is that the second derivative we have to find by taking the derivative of that. And again, we are going to use the quotient rule. So using the quotient rule, we're going to square the denominator. So that's going to be x squared minus 1 now to the 4th power. And then continuing with our numerator, we need the derivative of the top. So that's going to be minus 2x times x squared minus 1 squared. That was our denominator, original denominator, minus numerator, so negative 1 minus x squared, times the derivative of the denominator, and for this we're going to use the chain rule because we have x squared minus 1 quantity squared, so we're going to get 2 times x squared minus 1 to the 1st power, and then we multiply by 2x. And there is our second derivative. But it is not in a very good form for us to use to be able to do anything with it. So we need to do some simplifying and rewriting so that we can actually use this, because we need to figure out where the second derivative could be 0 or where it's not going to be defined. So I'm going to have to erase further up. I'm going to erase up at the top here. Leave our function up there. And in a minute I'm going to erase what we have down below, but we need to do some simplifying first. Okay, this first term there's really no simplifying to be done. The second term we've got some stuff we can consolidate or simplify, but before I do that, I want us just to notice that there are some things in common in the two terms in the numerator that we can factor out. We have a 2x right here, a 2x here as well. And then we have an x squared minus 1 in both spots, though we actually have a squared term there, so we're only going to pull one of those factors out. So I'm going to pull out the 2x, and from the first end an x squared minus 1. Now what's left from this first term, we're going to have the negative from the 2x, and then we still have an x squared minus 1, so we'll have quantity x squared minus 1. And then I'm going to subtract. We're going to pull out the x squared minus 1 and the 2x, and that's going to leave us with 2 right here times quantity negative 1 minus x squared. And yet more simplifying to do. So now we have 2x times x squared minus 1. I'm going to simplify inside these parentheses. And when we do that, we're going to have negative x squared plus 1, and then plus 2 plus 2x squared. And so overall, that's going to leave us with, in the numerator, x squared plus 3 as that last factor. And then we have x squared minus 1 quantity to the 4th in the denominator. And now we can cancel this x squared minus 1 to have a cube in the denominator. So overall, what did we get? 2x times the quantity x squared plus 3 in the numerator over x squared minus 1 quantity cubed. Okay. This looks kind of confusing now. There's our f of x up there. So here is our second derivative. So here is our f, and now we have our second derivative, which I'm going to write up in the corner, because what we care about is where that does not exist or where it's equal to 0. All right, that's not working. So f, second derivative is 2x times x squared plus 3 over x squared minus 1 quantity cubed. Okay. Okay, so we need where f double prime is 0 or does not exist. For f prime equals 0, we look at the numerator. So we're going to take our numerator, which is 2x times x squared plus 3, and we're going to set that equal to 0. So clearly we're going to get x equals 0 out of that from the 2x term. But then when we look at the x squared plus 3, this is always positive, because if we square a number, we're going to get either 0 if we squared 0 or something positive, and then when we add 3 to it, that's always going to be positive, so it's never going to be equal to 0. So from the numerator, we only get x equals 0. For the second derivative does not exist, we're going to look at the denominator. We want to avoid places where the denominator could be 0, so that means we have x squared minus 1 quantity cubed equals 0. So that means we're looking at x squared minus 1 is 0. So that means x would be plus or minus 1. So out of all of this, now that we've computed the derivative, figured out where the second derivative could be 0 or does not exist, we get the values x equals 0, x equal 1, and x equal negative 1. So those are the numbers that we are going to use to break up the number line. So I'm going to leave the derivative up there in the corner, the second derivative up there in the corner, and our function up there, and we're going to make the number line. So we have second derivative down below, function up above, and I'm going to break up the number line with negative 1, 0, positive 1. And now we're going to pick values in the subintervals to test. So in the first subinterval from negative infinity to negative 1, I'm going to choose x equal negative 2, and we're going to test this in the second derivative. So if we plug x equal negative 2 into the second derivative, in the numerator, for the 2x, that's going to be negative. For the x squared plus 3, that's going to be positive. That's always going to be positive no matter what we plug in. In the denominator, we're going to have x squared minus 1 quantity cubed. So negative 2 squared will give us positive 4. When we subtract 1, that's 3. So we have positive 3, and we're going to cube it. So that's going to be positive times positive times positive will still be positive. So overall, we end up with negative for the second derivative there. So I'm going to mark that. And that means that the function f is concave down in that segment. Now, moving on to the next subinterval between negative 1 and 0, I'm going to choose x equal negative 1/2. Going back to the second derivative, when we plug into 2x, we're going to get a negative. When we plug into x squared plus 3, that's always going to be positive. And now in the denominator, when we plug into x squared minus 1, negative 1/2 squared will be 1/4. When we subtract 1, that's going to give us negative 3/4. So we're going to have negative times negative times negative because we're cubing it. And so overall in the denominator, we get a negative. We have a negative in the numerator, so this is going to be positive. So f will be concave up in that segment. Now, between 0 and 1, I'm going to choose positive 1/2. We're going to plug this into the second derivative. In the numerator, that's going to give us positive times positive. From 2 times 1/2, that will be positive. The x squared plus 3 is always going to be positive. In the denominator, when we plug in 1/2, it's going to be 1/2 squared, which gives us 1/4. We subtract 1, that's negative 3/4. So we're going to get negative times negative times negative because we're cubing it. So in the numerator, we have positive. In the denominator, we have negative. So we end up with positive over negative will be negative over all. So that is concave down for the function in that segment. And then our last subinterval, we have x equal 2. That's the value I picked there. You can choose anything you want bigger than 1. And plugging into the second derivative, we're going to get positive from the 2x. We're going to get positive from the x squared plus 3. For the denominator, we're going to plug in 2. We're going to get 2 squared. That is going to be 4. Subtract 1, that's positive 3. So we get positive times positive times positive because we're cubing it there. So overall, that is going to be positive. So that means that f will be concave up in that segment. So our intervals of concavity. For concave up, the function is going to be concave up from negative 1 to 0, and then 1 to infinity. And then concave down, that is going to be from negative infinity to negative 1, and then from 0 to 1. Okay, so inflection points, we are looking for where the function switches concavity from down to up or up to down. So we see at x equal negative 1, there is a change in concavity from concave down to concave up. So if we think about x equal negative 1, that is a potential inflection point. But when we look at the function, we realize we cannot plug in negative 1 because that would give us a 0 in the denominator. So we do not actually have an inflection point there. Now, at x equals 0, we go from concave up to concave down, so that's a switch in the concavity, which means a potential inflection point. So we choose x equals 0, we plug in, we get 0 over negative 1. That is on the graph. So right here, we have an inflection point at x equals 0. And then going on to x equal 1, again, the function switches concavity from down to up in this case. But if we try to plug that into the function, we can't do that because that would give us a 0 in the denominator. So we actually only have one inflection point at x equals 0. And the actual coordinates for that inflection point are going to be x equals 0, and then we're going to plug into the function, and we're going to get 0 over 0 minus 1. So that gives us 0 over negative 1, which is 0. So our inflection point is at 0, 0.